and welcome to yet another Emerging Technologies for the Circular Economy lecture. Today is IoT, the data processing and big data part. So after we collected data, we communicated data, not just among sensors, but also we're ready to send it into the internet, into the cloud. That is now the topic of today. We're going to split it into two parts. I will do the first hour. Afterward, Anand is going to take over because I have to join the PhD defense and need to be there on time. And then afterwards, after a short break, the usual Q&A session where Anand will probably also give some updates on the issues that we had with CoCalc. Not quite our fault, but still a problem that needs to be solved because at the moment, quite a few of you are suffering from our CoCalc issues. But that's a topic for later, but I still wanted to get it on the recording so that people who watch it later also know that we're on it. Good. First, the same news updates / reminder as last week. It is time for the course evaluation. We have one QR code and link for emerging technologies, so for the computer science students, and one for the mining IoT students. So please take the time after the lecture or before next lecture to click either on the link or scan the QR code, and please take the time to evaluate. The lecture will also send a reminder via Stutterp just to be 100% sure that everyone gets it. Same as last week, please let us know what you like about this lecture so that we do not accidentally change it and make it worse in the next iteration, but also let us know what you like and what you do not like about the lecture or what you think could be done better so that we can improve that part. You do not need to list CoCalc as an issue. We already know that. We're going to address it and fix it and make it much, much better for the next iteration, but everything else where you like have any thoughts that can help us, please let us know. So the good thing so that we do not accidentally change it, as well as the medium and bad stuff so that we can do that better in the next iteration. That being said, let's move on to the actual course content. So we're once again at this nice overview figure. So in the past or in the first IoT lectures, we looked at the sensors, we looked at the actuators, the different types of sensors, different type of actuators, also some of the compute devices like Arduinos, Raspberry Pi, Iris modes, and so on. And in the last lecture or in the previous lecture, then we looked into different IoT communication protocols, similar to the sensors and the actuators and the compute devices. That was a selection. It was not a comprehensive list of all existing sensors, actuators, computing devices. And the same is true for the communication protocols. But we covered those that are most prevalent or that are a good mix so that you can say, okay, this is something from the more consumer perspective. So everything, maybe smart homes, smart watches, so consumer devices. But we also looked into more industry-like devices or something that's used in research. So protocols that you probably won't use at home, like LoRa or Sigfox. And then we also discussed, okay, where do I use which protocol? For example, if you categorize or cluster it by distance that you have to bridge either between sensors or where you can come from a sensor to a gateway, which then has a direct link to the internet so that we can go today to this magic internet, cloud, and IoT platform space where something useful is supposed to be done with the gathered sensor data. Because at the moment, it's just sensor values coming in. And now what for some smart home applications, if a certain value comes in, you know, okay, someone is at the door or it's time to water my plants. But this is like more of simple applications, not like the stuff where it really can make a big dent or a big difference in terms of what the IoT is capable of. First, we're going to talk about clouds. I'm very optimistic and positive that all of you have heard and used the term cloud and have a rough feeling that it's something magical that happens somewhere on the internet in big data centers. For the purpose of this lecture, we're going to look a little bit closer into, okay, what are clouds more or less precisely, what different types of clouds are there, and then slowly but surely making our way to IoT platforms as a specific type of cloud or cloud application, cloud service that can be provided, and also talking about the different types of data, specifically big data, and how it has to be handled inside this clouds and why we need clouds in the first place to handle big data. So there are, once again, millions of definitions. We'll provide you a few for the sake of the exam. It's only relevant that you can explain in your own words the core characteristics of a cloud. So the National Institute of Standards and Technology, something like the dean for us here in Europe, in Germany, is one of the standardization committees in the US. They define cloud computing or clouds as following. Cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, such as networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. So what's important here? Cloud is not just there is a computer or a server running where I can put a website on or some kind of application. Cloud also encompasses network, storage, applications, and services. So the whole package, not just some hardware somewhere. And the second part is that in contrast to you having some servers in your basement, there is a way to rapidly scale up and scale down depending on demand. So if your server in your basement or in our lab runs out of resources, we have to order a second one, set it up, install it, let it run in parallel to the first one. That takes time. In a cloud, it should be more or less instantly because you have fluctuating user demand so that you can scale up and down rapidly, more or less in an instant. So those are the first two relevant parts here. There are also various perspectives that you can take on what a cloud is. One or first attempt or first perspective to look at clouds is from the perspective of what do you manage and what does someone manage for you, because there are different stages of service provision towards you that you can take. On the left, on-premise essentially is the example where you have your server, your cloud in your basement or in our lab, where everything is managed by you. From the network, so you have to connect the server to the internet, and like if it's multiple servers, the servers among each other. Then you have to provide the storage, you have to provide the server itself, you have to put some kind of a virtualization layer between if you need it, so that you have, for example, if you're using something like Dockers or virtual machines, you have to provide that yourself. On those Dockers or virtual machines, you have to install an operation system. Then you might need a middleware, runtime, or data stuff to run your application. Also, you have to put all of that there yourself. This is like the most management effort for you. But if you do that, you can do everything as you like, but there's also all the responsibility on your side. You do not outsource anything. If you need more resources, you have to provide them. If something breaks, you have to fix it. If some unknown issues occur, you are at fault, you have to fix it. No one is gonna provide you any backups there. So on-premise, most flexible or most freedom, but also most responsibility. One step that goes more towards this first idea of a cloud and giving up some of the freedom, but also having less responsibility is what we call infrastructure as a service. So where you're essentially outsourcing and putting the infrastructure into the cloud. There, someone else is making sure that network, storage, server, and virtualization is taken care of. So you don't have to buy servers anymore. You don't have to put cables to connect them. You don't have to think about the internet connection for whatever you're doing for those servers. Virtualization is provided, storage is provided, someone provides all of it for you. And assuming that they have a large data center and doing this as a business, there's also always the option for you to just ask for more power or for more resources more or less instantaneously. That you can say, okay, thus far one server, 16 cores was enough. Now I need 4 times that power to do whatever I'm doing. Give it to me, and there's a good chance that you will get it relatively soon. However, you still have to take care of the operation system, middleware, runtime, data, and the applications. Everything that is still green is still your responsibility. You have to manage it. If you want to give even more or outsource even more duties, you can go to the concept of just platform as a service, where essentially the application itself could be a website, could be an IoT analytics platform, could be the backend of a smartphone app, you name it. You're just responsible for this application and the data that is related to that application. Someone else takes care of network, storage, service, virtualization, operation system, and just tells you, okay, this is how you install your service here, and this is where you can put your data and then run and work with your applications. Quite scalable model, but also the more responsibility you give away, the less opportunity you have to fix something yourself. If the platform is down and broken, there's not much for you that you can do. You cannot just plug in a different server and then you're fine. And something where you give essentially all responsibility away, software as a service, you are just consuming a software as a service. You're in charge of nothing. You are not responsible for anything. And there's nothing you can do if it goes wrong. So Teams, for example, is a software as a service. It's not even installed on most of your computers anymore. You can use it via a web interface. Same goes, for example, for certain web-based operation systems, where you have not just a single application, but a whole desktop application system in the cloud. You just go to an URL and you can use everything that would be normally on a full scale computer. Or if we stick with Teams, you can then use the Teams for communication. You can make video calls, you can write documents, you can send your emails, you have a storage container in the background, and everything is done and provided by the service. If Teams, once again, has a connection problem, then suddenly everything you are working on or that you need to work is gone and there's nothing you can do. So first perspective on this idea of cloud, from on-premise hosting to infrastructure as a service to platform as a service to software as a service, to see, okay, how much of the responsibility is still with you? How much flexibility do you have to still do something yourself? There are some layers in between that we did not list here. It's more about giving you a feeling, okay, there is a balance, or there are like different responsibilities depending on who is managing what, and that defines, or is one perspective to look on clouds on different levels. Some examples for on-premise, like it's essentially, as I said, the server, the application in your basement, what people did in the 1990s. What is infrastructure as a service? That is mostly cloud compute business. So Amazon Web Services, Microsoft Azure, or Google's compute engine. So they're providing you the hardware and you have to take care of the software, simple terms. Platform as a service could be Google's App Engine, where you have already it's like whole software stack running and you just have to develop an app, for example, using Google App Engine, and then you click deploy and it runs and you can get your customers on board. The Roku, OpenShift, they're doing similar thing just from different vendors. And then software as a service, we talked about Teams as an example, but all the Google apps, the whole Google application ecosystem, like Google Mails, Google Drive, Google Docs, Dropbox, Salesforce, Zoom, all the other stuff falls into this category. This very web conference that we're doing here with Big Blue Button is a platform, is a software as a service. You go to this website, click a link, you enjoy these lectures while we provide the lecture using this service provision. So it's a software that we use as a service. There are different billing models. We're not going to go into too much detail there now because it's a rather fluctuating market that changes heavily. It's more about giving you the idea, okay, for different categories and different things that you can look for to then figure out, okay, how much cost does it incur to use either some kind of a cloud system, being an infrastructure service, platform as a service, software as a service, versus buying a server and the required people to manage it and put it in my basement, because you have some costs there, which seem to be quite big on one hand, but then you also have to first, before you move everything to a cloud, you have to first calculate, okay, what is it going to cost me if I move my whole business into a cloud? Or as we can later see, there's also the option to just move parts of your business to the cloud and keep some stuff on premise while the other is in the cloud. Unfortunately, it is often not that easy to calculate that cost. On one hand, that is on purpose by the cloud providers or the software providers, because they make money telling you everything will be much better if you just host all of your stuff, your whole life on the cloud. But they still need to make the money. So there is. And as soon as you migrate it to the cloud, it's really hard to get back out of it. So you're more like, even if it's more expensive, you might be willing to just keep paying it because it's less of an effort than moving back to on-premise once you have sold all your on-premise servers. So there's, on one hand, a very intransparent way of pricing. So it's very hard to perfectly calculate upfront what you need to pay. And also sometimes it's really difficult to say, okay, how much resources do I actually need? Like how much network bandwidth do you have to buy for the application that you either already have or that you want to develop in the future? Like it's really hard to give a number sometimes for those information, or how much storage space do you need? How many servers do you need? So it's a mix of intransparency, which is by design, and then also uncertainty because you just don't know what numbers to put there. But assuming that you know those numbers, then there are a mix of different payment models. So for example, pay per use. You pay once for calling a certain API, or once in terms of, okay, I pay once to have this computing resource for a month, for a day, for an hour, for something. That's quite popular. There's also the combination of a base fee and pay per use. So you're paying $5 by default, no matter whether you use a cloud service or not. And then on top, you also pay something like per use. Pay per user is what you are probably most what is probably most known to you when you have like a Google account, an Apple account, a Dropbox account, whatever you're paying, or nowadays an LLM account, you're paying per user, per month, per year, or something like that. There's also the pay per transaction, for example, paying per data record stored to a database or per file being transferred somewhere. And pay per bandwidth or throughput is also relevant if you're talking about applications with a high amount of data. So someone has to provide the network capacity and bandwidth to allow Netflix to exist, for example. If you want to put 4K streams of various movies and series onto the internet to millions, if not hundreds of millions of people, someone has to run the infrastructure for that, not just from the compute power, but also pushing the data through the internet. And that person needs to get paid, or this entity needs to get paid. So especially for large companies who push a lot of data through the internet, there's also often a pay per bandwidth, pay per throughput fee that you have to pay and able to build. If you're just, I don't know, like two IoT sensors in a small website, then it's mostly pay per user, pay per use, or something like that. And bandwidth is not really an issue for you. There is also a quite big ecosystem in the background of all of those cloud stuff, where you, especially for the end consumer, are often only pursuing, like if you're only using the software as a service as your main thing as a consumer, you often don't really see, okay, what else is, what is happening there in the background? Because for most of you are probably have not been in touch with infrastructure as a service if you're not hosting your own applications that you're running on the AWS cloud, for example. Most of you have probably used something like Azure, which belongs to Microsoft and is essentially the back end for Teams and most of the Microsoft services, or you have used the Google Cloud by having been in contact with all the Google application systems. But if you're looking more at it from the infrastructure or the platform as a service provision, you probably haven't really been in touch with that. And this is actually a quite big market, even though now all the AI market is becoming much, much bigger, but the cloud system in itself is still a big thing, especially since you now can also get AI capabilities as part of the cloud ecosystem. So it's a extremely profitable, but also highly capital intensive market. And here we have two figures, one from the Q4 2021, which gives you the market share, and from the Q1 2026. And you can see that the market shares in itself did not really change that much. So AWS still the front runner, closely followed by Microsoft and Google. And then all the others are more or less niche providers with, yeah, we're still talking billions of dollars here, but they are more or less niche and not much has changed there. What has changed there are those numbers here. You might be slightly confused by the number of 2026 smaller than the number of 2021. There's quite simple reason here. This is the whole revenue of cloud for 2021, while this is just the revenue for Q1 2026. So if we take this times 4, it's a rough estimate. We're talking about $520 billion compared to $178 billion in 2021. So that's quite a increase in revenue. So there is still a huge amount of money to be made in this cloud business, especially if you're one of the big providers. But you also have to build a lot of data centers, provide the infrastructure, take care of electricity, and so on and so forth. So there's also a lot of upfront cost. But this was just like as a background information for you to understand, okay, who are the big players and what are we talking about business size here? So AWS, Azure, Google Cloud being the front runners running most of the cloud empire nowadays. We have brought you one example, one explicit example for to illustrate, okay, how complicated can this pricing thing be for a rather simple use case. And the example that we brought here is the AWS Glacier. Glacier is something like a backup Dropbox that you only use every now and then to put a backup there, and you just keep it so that it's really safe. So Glacier is something where you put important data, but only for the case that your main hard disk, your main storage space dies. So you never intend to use Glacier, but it's there in case everything else goes wrong. And that is essentially the business model or the idea behind this Glacier. It's a It's not something like Dropbox or like your Proton or Google Drive where you can instantly click on a file, you see it, it's a wrong image. Is this the right one? Yeah, okay, this is the right one. Now I will look at this or watch this video or whatever. It's really for, okay, it is somewhere and it takes a while to retrieve it, but it's safe. And this is essentially the application case for AWS Glacier. So if you want to put, like if you're a big company and you have to put all your accounting data somewhere or backups of all your important files and so on and so forth. And before you put everything into AWS Glacier, of course, you check first the functionalities. Does it really provide all the stuff that I need? Those of you who've done requirements engineering with us know how to start this process. But then you also calculate the cost. Okay, let's say I have 50 terabytes. So how much does it cost me to store 50 terabytes? Okay, I get a storage price of 0.0045 cents per gigabyte. So 1 terabyte is 1,000 gigabytes times 50. That gives you a price per month, which is even for 50 terabytes quite small. So 450 per terabyte times 50, that's not really that much. So storage pricing in itself, quite simple, no problem. Problem occurs the moment you want to get the data back. While it only costs you 0.0045 per gigabyte per month to store it, getting a gigabyte back is a completely different story. And now we're getting to like one of those examples where it's being intransparent by design and quite difficult to get to a proper number because there are different retrieval times. How urgent do you need your stuff suddenly back? And the slower you need it back, the cheaper it is. And there are also some like if you get this and this to package together, blah, 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 then it's easier and cheaper to get it back. But you can see vastly varying retrieval prices per gigabyte. So the most expensive one costs you 3 cents or almost 4 cents per gigabyte. And if you calculate that back to our 50 terabyte example, that is suddenly a lot. But usually the moment that you actually need that data, it's so urgent that you pay every price. And then there's also another cost on top of that for the number of requests that you're sending to AWS Glacier. If you're lucky, you have one big 50 terabyte file that you can just download. The downside is you have to pay really everything and retrieve everything, but you don't have to send a lot of requests. However, if the 50 terabytes are split into 50 million files, then you have to request 50 million files and you pay $12 per 1,000 requests or 3 cents per 1,000 requests, depending on how urgent you need it. So that is something that's on one hand quite transparent because you don't really know what you get and what does it mean like that you get it more or less instantaneously and what does slower even mean. But also it's really hard to tell upfront how much of that data do you need, how fast, and how many requests will that be. And you have to play through different scenarios to then get to the actual costs of putting something into AWS Glacier and then also getting it back. Quick side note here, please don't trust us exactly on those prices. They might have changed since they updated the slides. I don't know for sure what the exact prices are now, but you get the gist of why we're showing you this slide, because it's an integral part of using any cloud service to try to best estimate the costs that it creates when you have to rely on some kind of a cloud infrastructure so that you can compare hosting everything yourself to infrastructure as a service, platform as a service, or even software as a service. There are some calculators which supposedly help you, but they are quite specific for certain services, and even they leave a lot of intransparency behind. Or there's still a lot of intransparency once you've done them, but at least they exist. And if you ever find yourself in the position of having to calculate the cost for using a certain service, please look for them, especially for Google, AWS, and Azure. Those are not too bad. So far we looked at the cloud based on what do I manage, what does someone else manage for me. Next perspective is who or where is the cloud situated? Because I briefly teasered that you can maybe choose between having something on premise with you and something on the cloud on a different level, either infrastructure, platform, or software as a service. And those differences are essentially then called a public cloud, where services are available for public users, but everything is somewhere with someone else. Private cloud is essentially a closed private infrastructure, mostly on premise, so with you. And then you can also have hybrid models like hybrid clouds, where you have a base cloud running on your system on premise in your data center, but being designed and structured in such a way that if you need it, you can get resources from the outside, like AWS, Microsoft Azure, whatever, to provide resources at peak time, get them when you need them, and then scale back down when you don't need them. So think about maybe something like Christmas shopping for shopping center, not for shopping centers, but for online shops, for example. Usually throughout the year, you have enough resources to sell your honey yourself just with a small server in your basement. But around Christmas time, people get crazy for your cinnamon honey, and suddenly you're getting 500,000 requests per minute, and your small server in your basement can't handle it anymore. So you buy extra Amazon resources to sell as much cinnamon honey as you can until you're out of stock. Simplified example, but you get the idea. The second part that is inside this categorization is who is the service available for, or are the services hosted by those clouds available for. So in the public cloud, this is a service that's available for public users. So that could be software as a service. Example here with LLM models. So ChatGPT, Claude, whatever, being services that are available for public users hosted on a software as a service cloud. Private cloud could be an LLM just hosted for university students, or this web conference system. It's built with an existing private infrastructure, and it is limited to a certain group of people. StudIP, Moodle, same stuff from the service provision perspective. And then a hybrid cloud, something where I mix both of them, and then there are also this niche topic of community clouds, where you have different types of cloud that are integrated together to meet a common or particular need for a multitude of organizations who come together to do something. That could be public, private, or a mix of them again. That gives you different parameters that can vary, like scalability, reliability, security, performance, cost. But those are very broad and vague descriptions. For example, if you take security, why should it, like, you can argue that a private cloud is more secure than a public cloud. But if you have a shitty cloud admin in your basement, in your data center, at your company, then it's for sure not more secure than a public cloud. So take them as orientations, but not as cast in stone facts that are undeniably true. Good. Yeah, this is essentially the question marks indicating what I just said. Good. Whenever you're putting something in a cloud, mostly in the context of the Internet of Things, we're talking about data. So first of all, sensor data that we're collecting raw, and then later processing them to gain some wisdom, some knowledge, some information, some interpretation out of this data. And the question whether you can use any cloud service in the first place that is not on premise is essentially answered by the type of data that you're collecting. Because the GDPR, General Data Protection Regulations, clearly outline certain rules for certain types of data. So if you're collecting temperature and soil moisture data from our greenhouses, there is no privacy protection necessary, and security is also a secondary objective, because yeah, what if someone knows what's the temperature in our greenhouse? Not really a lot of damage that you can do with it. However, if you're collecting data from and putting them in the cloud from smartwatches that give you personal information, like where is a person going based on the GPS of the smartwatch, what is the heart rate of a person, what's the blood pressure of the person, what's the general health information of the person, you're getting in this GDPR territory. If you're talking about specifically health-oriented IoT devices, you are definitely suddenly in the range of patient data. You cannot just put patient data in a public Dropbox or in the cloud without adequate protection. There are regulations in place what those clouds need to prove to be able to do in order for you to be allowed to put patient data in the cloud. So am I even allowed to put the data that I want to put there in the first place? And if I'm allowed to put the data there, in what form? Can I put it there as raw files or raw pieces of information, like our temperature data? Or do I have to anonymize, you get the idea. This data, do I need to encrypt it and are only allowed to retrieve it, decrypt it, and then locally process those files? Am I allowed to transfer this data to foreign servers? Because this problem or this conflict zone of the US government essentially arguing that every server that is somehow owned by Microsoft or any US company, no matter where this actual server is accessible to the US government, obviously doesn't really sit well with a lot of people who are not in favor of the US government. So at the moment, the US government thinks or argues every server that belongs to a US company like Microsoft should be accessible to them. Doesn't matter if the company's server is actually hosted by the German subsidiary of Microsoft and being on German soil in a German data center run by German people. That doesn't matter to them. At least that's their point of perspective. And you might be not so worried about that now from the US perspective for whatever reason, but you understand this idea that if you put something in a cloud, you don't know for sure where the data is. Like, what does it mean that I put it on the cloud? Where is the data center actually hosting this compute power and also the storage? For some cloud providers, or for most cloud providers nowadays, you can select certain zones, and depending on how specific your needs are, you have to pay an extra price. Because for Microsoft, for Amazon, for Azure, for Google, it's much easier to promise you, yeah, we'll somewhere keep it on this planet, because then they can shift their resource balancing as they please. So if there's a lot of free capacity in Africa, you can put some of your stuff there. If more compute power is available in North America, you can put something there. So that's usually the easiest option for all cloud providers, that they just ask you, is it fine if I put it somewhere on this planet? For some data or for some services, for some company, it has to be within a specific region, so they can sell you something extra by promising you, okay, it will stay within the EU. Or if that is not specific enough, you can also pay extra to get the promise that it will stay in Europe. Not in Europe, specifically in Germany. So if you have some applications that have so specific constraints that they need to be within Germany, for example, for German government cloud services, then you can even get that as an extra service. If it then really is in Germany, it's somehow difficult to prove. But those big companies are going to promise you, pinky swear, that this is true. Another issue to consider is the question of liability. Who is responsible in terms of data loss? So if your data gets lost, or if data is manipulated either on purpose or by accident. Usually the service level agreements specify those information, so it makes sense to read through those before you start putting your data there. And to also understand, okay, am I liable? Is Google liable? Under what circumstances is Google liable? Because if something is wrong with your applications, your customer first sued you, and then you might get your money back from Google or not. Who has access to the data on the part of the cloud provider? Essentially goes or boils down to this question or to this example of the US government that I gave. Can the cloud provider look into your medical data that you're hosting for your patients? Can some third parties access it, or some secret services? Might be relevant for some applications more than for others. And then those cloud services, the service level agreements that also cover this liability issues in the event of data loss. They also cover what happens if cloud services are unavailable. Usually there is a 99.999 and then something promise that they are online 99 point whatever percent of all the time. So that means, I don't know, half a day or a day of downtime per year, which is fine for them. And you have to ask yourself, is that also fine with me, that throughout the years there are times where stuff is not available, or do I need to pay for something to get close to 100% of online term per year? And if that doesn't happen, I get compensation money or so. While most of you know clouds as something that someone provides to you, using this example as software as a service, Google Docs, Zoom, this video conference, there are also options, and it especially is probably known to the computer scientists among you, to host certain cloud services yourself. So you, for the TU Clausthal students, you know potentially the TU Cloud, where you have 5 gigabytes, 20 gigabytes of storage, where you can put files, access them from wherever you are, and then use them to download them somewhere else, and so on and so forth. That, for example, is a so-called Nextcloud instance. So the university uses a Nextcloud in the backend to provide you the service under the name of TU Cloud. It previously was an own cloud, which is a similar thing, but nowadays it's a Nextcloud. You can also just download it, install it on your Raspberry Pi at home, and then have something like a Dropbox yourself at home. You can also run it on your computer. You can scale it up to terabytes, if not petabytes of data. So there is essentially a way for you to also run small size clouds yourself. Cloud is nothing that only big companies can host. And SingSing and so many others are just examples. They're all now from this data sharing ecosystem, even though Nextcloud and OwnCloud also can do something like Google Docs. But this is now besides the point. It's just to showcase most cloud services are provided by big cloud people or entities, but you can also do it yourself if you have the skills to do so. So the self-hosting is actually an option. You can also categorize clouds in terms of how self-hosted are they and how much do they allow in terms of self-hosting as a categorization as approach. So we have a two-dimensional system. There are probably more dimensions to it, and some dimensions might be more important to you than others, but this is just to give you an example here. On the y-axis, we have the infrastructure provision at the bottom, and data center virtualization on the top. So we're essentially scaling between the different cloud models here. On the x-axis, we're ranking flexibility from low to high. AWS as one example being on the very inflexible level, and on the infrastructure provision part, while like a virtual cloud would be up in the data center virtualization, still a little bit unflexible. And then there are like 4 examples that we put here to give you different, call them software collections for cloud hosting, for different use cases that are all open source. So eucalyptus, for example, is not just a tasty plant, but the name of a software ecosystem that allows you essentially to host your own AWS compatible cloud. So it is more flexible than the bare AWS cloud, where you're completely dependent on Amazon, but it also is only on the infrastructure provision level. So it essentially provides you, or the computer scientists among you, the equivalent of an AWS EC2 system, so the Elastic Compute Engine. That is what you get with Eucalyptus, and then you can build everything on top if you like, or you can become a competitor of AWS if you like. But this is what the Eucalyptus cloud, for example, is for. OpenStack, slightly more flexible, but also way more complex. This is, for example, I think OpenStack or OpenNebula is what NASA used to use. Not sure if they're still using it to host their clouds internally. So highly complex, super configurable. You can do God knows what with those clouds, but it comes with a very high technological cost. But you can run your own cloud with that. CloudStack, OpenNebula, quite flexible, also super complex to configure and to use, but going more in this direction of, okay, I have a data center, I want to virtualize it and essentially use it and make it act like one cloud as a whole. So point being here, there is open source software for self-hosted clouds out there. It usually doesn't make sense as a single person to look into Eucalyptus, CloudStack, OpenStack, OpenNebula, and there are like many, many more. But if you are, as people working in potentially in the future in the industry, are tasked with understanding the different computing clouds that could be hosted by your company yourself, then this is like a starting point to look at those different cloud models and the varying flexibility. But as I said, there are like more dimensions to this. This is just to make the point of an example, and it also doesn't really serve a purpose now to rank and compare all available cloud softwares now, because this might be outdated in a year from now. What we are building towards too in this course is a specific sub-ecosystem within the cloud ecosystem, which are the specific IoT clouds that we're interested in. So clouds that are specifically designed and tailored to the needs of IoT applications and the IoT ecosystem. So something where it's already expected that data goes in, then some magic happens with the data, and then I build an application on top, I run analytics on top. So this is what IoT clouds are for. That encompasses some of those domains listed here. Once again, not a complete list, but for you to get an idea. So application development, meaning applications that are built using or in the context of the Internet of Things. Managing devices in my IoT network, so that if I have 5,000 temperature sensors, I don't have to manage every single sensor separately, but I have a nice management dashboard or capabilities. The system management, so not just the device, but the whole system. Heterogeneity management, if it's not just 5,000 temperature sensor from the same vendor, but maybe from different vendors, and then also not just temperature sensors, but also soil, humidity, wind, sunshine, whatever sensors. So I probably have quite heterogeneous set of sensors, the more complex my scenario gets. Then you also want to manage all the data that it receives, because it's probably not just temperature data in Celsius, but also soil, moisture in percent or in a certain unit, humidity in percent. Is it relative or absolute humidity? Is it maybe also a video stream from your plants growing, which is then not a number or a string, but rather a video? Maybe you also have audio, then you have other sensor data, so you also need to manage your data. Then you have to analytics to make sense of your data, something that we'll cover later. Deployment management, closely related to device management. So you have a device ready, being either now deployed into your environment, so putting a sensor in our greenhouse or somewhere in the forest, or deploy further edge and fog computing compute units. We'll also get to that later. Everything that is somehow related to deployment. Then monitoring. Is everything working? When did I hear the last time from temperature sensor number 25? It was supposed to report once every hour, but I haven't heard from it since yesterday. So clearly something is wrong. Or am I suddenly getting weird sensor information? Usually the maximum temperature in our greenhouse is, let's say, 40 degrees Celsius, and suddenly it reports constant values of 80 degrees plus. So either someone made a nice steam sauna out of our greenhouse, or the sensor might be broken. Then visualization of data being somehow related to analytics, but also a separate topic. And then research in general as a broader catch-all phrase here. Just to give you an idea, what is all under this banner of IoT cloud platforms? What are different things that they are supposed to do that are specifically tailored, in this case, towards IoT applications? Not a complete list, but I hope it gives you an idea. So what is an IoT platform exactly? They support, or they are support software that connects everything in an IoT system, thereby facilitating communication, data flow, device management, and the functionality of your IoT applications. So they connect your hardware, your sensors, your gateways, your edge and fog devices, your compute devices like the Raspberry Pis. They help you to handle different hardware and software communication protocols. So the Raspberry Pis communicate via Wi-Fi, or LoRaWAN sensors communicate via LoRaWAN. They still all end up at some point in the same cloud. They provide security and authentication for devices and users so that you don't have to do that yourself. How do you make sure that only your sensors feed into your IoT application and not the sensors or the fake sensors of a competitor who tries to fuck with you? They help you to collect and visualize and analyze your data, and they also allow for external web service or application integration so that you can also integrate existing applications of yourself or from someone else, which you then can use to provide services yourself. So there's quite a large bandwidth of what IoT cloud platforms can do. Important here is they don't have to be able to do everything. There are also specifically tailored IoT clouds who can only cover a subset for a specific need. It's not like every IoT platform or cloud platform has to provide all of this here. There are quite a few IoT-specific cloud platforms out there. Some of them die, some new emerge, some stay relatively stable but undergo changes. You won't be surprised that most of the big IoT, of the big cloud players have some kind of a specific IoT cloud. So AWS has something, Microsoft has something, Google also has something, but it's not listed here. And then also IBM, Samsung, ThinkSpeak. So it's, yeah, there are multiple providers out there. We made a minor overview / comparison for you, but I would like, it's missing the self-study star, but I would leave it as a self-study task for you to take like 2 or 3 minutes to go through that table yourself, because it also doesn't really add anything if I'm just reading this out loud, what's written here. It's essentially, once again, for you to get an intuition for what's out there and how can those platforms differ in what services they cover and what they exclude, and which then gives me different functionalities which might be relevant or irrelevant for the IoT application use case that you might have. This is a example now for the specific AWS IoT cloud that they provide to illustrate an industrial application example. And what you can already see here without the need to understand all the different subservices here is that even the IoT cloud provider sees this not as just, okay, you need one thing to do this, but they subdivide it into different IoT cloud services that they chain together or cluster together so that they can cover the whole data processing pipeline that you may need. So you might have your industrial equipment somewhere with a data server and the historical database. And an operation system like FreeRTOS, that's not the point or not relevant for now. But the first contact point for you is then AWS IoT Sitewise, which helps you to collect, process, and monitor your equipment locally. So you get an AWS software package or service thing that you have to put on your local devices to manage them. Then you also have AWS IoT Greengrass, which run application code specifically tailored to the AWS IoT cloud at edge devices. What edge and cloud and fog devices are, we'll get to that in a second, so please bear with me. But you also have to put that at your place. AWS IoT Sitewise then reports to the data management part on the cloud of AWS IoT Sitewise, while the IoT Greengrass part then connects to other services in the AWS ecosystem like IoT Core, IoT Device Management, IoT Device Defender, IoT Things Graph, and then all putting it together later in the analytics and event detection pipeline, where they offer you, by chance, also the AWS IoT Analytics and the AWS IoT Events functionality. And for each of them, you can figure out, do I pay per use? Do I pay per transaction? What's about network and bandwidth? Do I have a base fee? What's the service provision and so on and so forth? So you have to figure out all that yourself because they don't want you to get everything in one, but rather as separate things, which on one hand, like it's not all bad, like I'm over exaggerating a little bit, because it increases highly your flexibility on what you need and how you want to connect it. So that's like also a nice pro, but it can also be a con, depending on how you look at it. Yeah, so highly specific, tailored services provided by just one cloud provider to cover the whole pipeline instead of doing it with one service, thereby highly configurable, highly flexible, but also very difficult to manage and wrap your head around it, and then also get to some kind of cost estimate before you get it up and running. And of course, you have a tremendous vendor lock-in with most of those scenarios or with most of those providers, because once you're in their ecosystem, have connected all of this and got all your data in there, it's very hard to get back out and just go to the competitor. So choose wisely before you do that. Just an example to understand, the AWS IoT cloud is not just one big thing. It's a composition of different specifically tailored subservices that help you to achieve your needs or to achieve your goals. For connected homes, there are different or similar pipelines that you can use if you are someone who would like to offer those smart home services to your customers. Of course, you can also do that yourself, but usually that's a little bit too complicated for everyday users. And there are also free self-hosted versions that are more cheap, like Home Assistant for you. But that's a different story. Good. Anand, I'm slightly behind schedule, so I would need you to unfortunately take over now because I talked a little bit too much and won't make it just until the big data point. I'm really sorry about that part. Good. I will leave you in the professional hands of Anand and Chintan, and thank you very much. You will have me back by next week. Enjoy the rest of the session.
So, without further ado, Let's continue the lecture with edge and fog computing. So I think I also have to take a presenter from Benjamin. Yes, okay. So first of all, coming away from the IoT cloud. So we know about cloud services in general. We've also talked about IoT cloud. So why exactly do we need this new concept? So we already talked a little bit about edge and fog in the last lecture when it comes to privacy and security. But now we're going to talk about exactly why we need edge and fog in the first place. So specifically for IoT problems, a lot of the time the amount of data you are generating is just way too large for you to not just store on premises, like the place where you're generating this data, but also, so you just do not have the processing power or storage amount to keep it there, and the network latency. Maybe you need to have decisions that need to be made very quickly, and you don't have the processing power to process this large amount of data to make those decisions really quickly. So you cannot really transfer them to the cloud because you don't have that type of network latency issue. So it takes a lot of time to transfer this large amount of data, even if you can transfer it. And then making those decisions again, this takes a long time. Also will take a lot of cost. So if you need to make a decision based on a few gigabytes of data, Benjamin talked a lot about how every single thing you do on the cloud costs some amount of money. And if you have to do this on the cloud for large amounts of data, you need to pay for transport of this data and then also for the processing of this data. And then, of course, there's even more limitations on top of this. And basically, what we try to do is to put something in between the IoT devices and the cloud devices. So basically, shifts some of the computing capacity from your central servers or the cloud closer towards where the IoT devices are placed themselves. So basically, you are having something that is more performant than a tiny Arduino device or a tiny microcomputer or microcontroller that can do some amount of data processing much faster than the cloud can do so, because you're saving some amount of network data travel and also some amount of money, obviously, because you don't have to pay for this additional cloud service for some of your computing needs. And yeah, so you have faster data processing at your edge, a shorter response time because it's closer to your actual IoT devices, and also it's saving your bandwidth with regards to your cloud server. So like we said, this is kind of what it looks like. You have your IoT devices, which are doing very, very, very tiny amount of data validation when it's collecting this amount of data. And then there's the cloud, which canonically would just take all of this data and do more extensive analytics and processing, and then the edge basically comes in between them. And basically does more complex data validation the cloud cannot do due to the various issues that we did explain before. And then some things which doesn't take a lot of time or which are cheaper to do with the cloud or not possible with the edge anymore, it can forward it to the cloud, or store it for a certain amount of time until the cloud is there that can process it later on. So it can store some data for some amount of time and send them. Maybe you can pay for a slower transmission rate for things that are not very time limiting or have very strict time constraints, and then over time process the data and then give you a result a bit later than you actually need it. One example is this thing called Foghorn. So where they used the edge model quite well. So they had a challenge. Essentially, it's a type of implementation used to create these so-called smart buildings, where they have a lot of elevators and escalators. So elevators that are the ones that go up and down multiple floors, and escalators which go between half floors or half floors, like stairs, basically. And this company had a lot of these elevators and escalators deployed globally. But the problem is not in every infrastructure or type of building, you cannot have the same expectation that you will always have a certain amount of bandwidth to communicate your data generated from these big machines like your elevator or your escalator. Like, okay, um, what's the sensor amount for the number of people going up the elevator? What's the performance like based on the number of people transported per month? How often does the elevator break down? And try to correlate this with the number of people using the elevator or the electricity cost and so on and so forth. In general, the challenge is to mine all of this sensor information to get some insights out of it, and then reduce inspection repair keys. So basically, every time you have to do an inspection or to do some kind of repair on the elevator or escalator, you basically have to pay a certain amount of money for not just your mechanics and your technicians, but also you might have to like close down the elevator for a while. Maybe if this is a business or some kind of a mall or something like this, it might lose some amount of that business because people have less time or less opportunities to go up and down into this building. So that's also something that they have to take into account. So you really want to reduce the number of times you inspect these elevators or have to repair them. So basically they want to do something like predict when your elevator is going to break down or needs an inspection, and then make sure to send people beforehand. So, but the challenge with this is that you cannot really send all of this sensor data directly to the cloud, and neither can you expect that you have all of the processing happening at once. So what they did is they installed the existing sensor kits that they had, which sensed all of the different actions that are happening and different motion events that happen. So about a less than 1 gigabit footprint of this foghorn system. And then basically used something at the edge that basically aligned both the time and state of activity data and just added like a few lines of C code, and then use about 40 plus machine learning model to generate more predictive maintenance alerts. So it's not scheduled maintenance anymore. You basically just have a tiny amount of extra processing that you are installing on the existing systems that you have on your infrastructure that does some amount of the processing instead of sending it to the cloud or instead of sending technicians to over to do some of that maintenance. So they're basically able to do a lot of predictive maintenance and smart instead of having to do it at scheduled intervals, which reduce a lot of their repair and increase their revenue. So we haven't defined edge computing yet, and basically it refers to enabling technologies that allow computation to be performed at the edge of the network on downstream data. So downstream data basically is data that's coming from your IoT devices, and do this processing on behalf of the cloud services, and upstream data on the behalf of IoT devices. So also does the other way. So if the cloud needs some processing to happen that the IoT devices are not able to do, at least not in a timely manner, the edge computing devices would do that. In this example that we just looked at, the edge device would do some kind of machine learning inference model and run it based on very recent sensor data, and then send back something to the cloud that says, hey, we don't really need, we didn't really use the elevators that much in the last month, so we don't need to have a scheduled maintenance this month because it wasn't really used, as an example. So close to edge is also something known as fog. So the actual foghorn system is basically named after this word called fog. So it's very similar to the concept of the edge, which is a bit more abstract. Fog is basically where you have a geographically distributed computing architecture with a resource pool that contains more than one or more ubiquitously connected heterogeneous devices. So you have different types of devices that are distributed across a giant geographical region, similar to Foghorn. which some of those devices can be edge devices, which are at the edge of the network. Some of them can be even between the edge and the cloud. And these are not exclusively seamlessly backed by the cloud services. They somehow do some more work on their own without the cloud having to intervene, and sometimes also work collaboratively to provide more elastic computation, storage, communication, in very isolated environments. So, for example, when there's a building infrastructure where having a set amount of bandwidth is not guaranteed, and also onto a large scale because they are in many different geographically distributed regions. So you can do the same type of tasks in a very large scale in different types of architecture at the same time to a large different number of clients in proximity. So it sounds very similar, like edge is something that comes in between the IoT devices and the cloud, but also the fog is also something that comes in between the edge and the cloud. So what exactly is the difference? So there isn't really a concrete definition where you can differentiate the two of them. You can say there are general amount of characteristics of a system that makes them either edge or a fog, but depending on who you ask, it's really hard to give a very certain answer of exactly what something is an edge system or a fog system. But you can create like a general pyramid that gives you some kind of an idea to how to situate this concept. So you can understand the IoT cloud. So you can have maybe thousands of cloud servers, let's say, that then are storing a lot of the data long term, have a lot of backups, making sure that this data never goes away, is never corrupted, but of course costs a lot of money. But on one step lower than this, then you have your fog systems, where you can have, because they're lower cost, you can have millions of them. Some of them are collaboratively working to share data, share processing, sometimes share some analytics, also communicating back to the cloud for maybe long-term storage when you don't have the resources anymore at the fog to store this data. And then on the edge, you have more, like in these terms, billions of edge devices, because these are the actual things which are situated very close to the actual IoT devices at the edge of the network. So the very end of this pyramid are these edge devices. So because there are generally a lot of IoT devices, so your smartphone can be considered an edge device that is communicating to maybe fog or cloud servers about IoT devices, like let's say your smartwatch, maybe something about your smart fridge. So your smart fridge may not do any computing of its own. It maybe only communicates some information to your phone, and then your phone can do a lot of computation without connecting to the cloud server or the fog server. But then at the end of the day, at some point, your account data, your purchasing, and all of that just goes to the cloud and then comes back. Similar stuff you could say for, let's say, trains and EVs or other smart car fleet management systems. Some more very interesting information and how this works with Amazon. So there's a so-called Lambda, which is called serverless computing. As you can see, the self-study star. We are not going to go into too much of detail in the lecture. So basically, this is something that you need to look up on your own time. And they also have edge-based systems that are compatible and work with edge scenarios. But we are going to compare some of the other Amazon services and compare how they are, the different functionalities that they have and the type of applications you might use them for. So there's a so-called Amazon Snow Cone, which is more of an edge computing or data transfer edge storage device, is what you would use it for, compared to the Snowball edge storage optimized one, which really doesn't do a lot of computing, but it's more for optimized towards storing and transferring data to the cloud. And then you have the Snowball Edge Compute Optimized on the other side, where it basically, instead of doing a lot of storage, it's doing a lot of computing and data transfer. And then at the other edge, you have this thing called Snowmobile, which basically all it does is transfer data. And these things, based on their usage scenarios, they have different, very, very, very different types of different parameters. So let's say, for example, in terms of usable hard disk storage, because Snowcone is kind of doing all of these things here. They do like have a 8 terabytes of hard disk storage, but no SSD storage. But on the other hand, the storage optimized edge devices really have a lot of edge storage and maybe also some amount of SSD storage, because you want some amount of more reliability with your SSDs, and maybe your HDDs are used in some kind of a RAID system where you have a lot of duplication, so you need a bit of other more reliable storage in this case. And then you see that the compute optimized node has actually a lot more of terabytes. Or maybe this is because you need maybe some machine learning models which require a lot of storage to be situated in your system. But of course, you don't store a lot of data as much as the edge storage optimized edge systems. On the other hand, on the other side, you have the data transfer nodes, which just store a lot of data in house, but never basically have any kind of SSD storage, because that is very, very expensive compared to hard disks, and just transfer that data. Now also you can see a usable memory of, obviously the compute optimized ones have a lot of RAM available for them, because they need to compute a lot, and for storage generally 80 gigabyte depending on the size of files that you exist. And obviously you can also have access to some GPUs to do some GPU accelerated machine learning models, for example, and also a lot of different other parameters which are really, really important to take into consideration when you make a decision of what type of edge device I want to use for my system. So we talked a lot about IoT clouds, edge and fog clouds, and a lot about the data that's being collected. It's basically a lot about how we can create your infrastructure in terms of what kind of hardware you can put close to your IoT devices, and how do you process this data, what type of cloud services you can purchase, what type of cloud services exist to process your IoT cloud data. But basically we need to also talk about what do we do with this data in the first place, and how do we manage and store this data in a way that makes sense for your application. So we know this concept of big data is something where you might misunderstand and think, okay, big data basically means that we have a lot of data that we are storing in our server, and this basically is big data. And the more data we have, it means it's much better. But this is kind of not always true. Knowledge is not the same as data, which is why just having blindly a lot of data inside of your servers, or collecting a lot of sensor data, is just not always the good thing to do, because you may be just paying way too much for storing some information which you really don't need to do. And it really depends what you're doing with that data, which decides whether that data is justified in being collected in the first place. So there's a lot of definitions for big data. We are going to stick to this one, which basically calls it something that represents the information assets, which are characterized by such a high volume, velocity, and variety to require specific technology and analytical methods for its transformation into value. So it's not something that we needed something very specific to the case where you have high volume, velocity, and variety of data coming into your, let's say, cloud servers or your edge and fog systems, where you need to use specific technology and analytical methods. So the ordinary methods were not really enough to convert this data into knowledge, or by transforming it into something that you can actually value. So you need to really create something new, and in this case you call this new piece of technology the big data technologies. So these large and complex data sets which you generate from your sensor data are so massive that your classical data processing software really cannot manage them. And you really still want this data because the value that you had from this information and new knowledge by processing this data will offer new solutions for existing problems that you have. And in general, when we talk about big data, you have this thing called the 4 V's of big data. So the 4 different characteristics of data or technical systems that handle this data that characterize around something that's known as big data, this umbrella term. So these are firstly volume, velocity, variety, and veracity. And we're going to talk about all 4 of these one by one. So volume, just as the name suggests, is basically when you have large amounts of structured and unstructured data from various heterogeneous sources. So basically something where you just have to store or have to process like several terabytes or maybe hundreds of petabytes of data. That's a lot of data. Is something where you can call that's a big data system. But also when this data is coming really, really quickly. So the rate at which new data is being generated, let's say from a camera, or which is capturing a lot of video. So depending on the frame rate that you're capturing, the type of compression that you're using, you have a lot of speed in which data is being transferred and then also analyzed maybe by machine learning models. And at the best case, you can process the data faster than you actually generate it, which means that you don't have to store the data anywhere while you process it. And this basically means that once you get the data from your sensors or edge systems, you can process it while it's being generated and don't have to write it in an intermediate location before processing it. But of course, it's not always true. So you need really specific solutions that can handle the velocity of data that you have with big data systems. So variety, on the other hand, it comes with the heterogeneity of data. So different types of data that's coming towards you, which can be structured or unstructured. So we looked at, for example, in exercise 4, I believe, or exercise 5, where you have different types of same data, basically weather information coming from different sources that is structured similarly, but also coming in different formats. So this is, in this example, it was not big data because it was just a little bit of weather information. But if you were collecting this data over 10 million times a second, maybe you're getting sensors from your weather station that collect sensor data from your wind conditions, your air conditions, water conditions, or humidity. And if a lot of data is being generated from different sources about the same amount, this is something that only big data systems are especially capable of processing. So even though you have a lot of data, you also need to make sure that you can trust this data. So once you are collecting this large amount of data, sometimes really quickly, it needs to be processed quickly, but also collected from different types of sources, you also need to know how accurate it is. So if you don't have good quality data, you can't really do a lot of information processing from it. You cannot gain as good quality knowledge as you could have with better quality data. So good quality data gives you good quality knowledge out of it. But if you have lower quality data, you can sometimes compensate for this by using a higher volume of it. But the challenges always come with something like if you're trying to create a system which has, let's say, dumping the last all of the tweets from the last 1 years to train some kind of a natural language model, then you are left with a lot of tweets where people are using different abbreviations or making mistakes. So this is lower quality data, so that kind of gives you some errors in the knowledge that you will gain from it unless you particularly try to use some extra processing to remove these things existing. And also from there, you also have politically biased data, for example, where the data you're getting from, let's say, Twitter may not be exactly accurate because it's biased by the political leanings of the people who are generating this data. And also you need to kind of detect and filter all of these noise and abnormalities when you're generating them so that you are gaining all the quality from this data that you could possibly do so. So all of these four different things are part of this umbrella term known as big data. Some challenges when it comes to big data. So let's take this example of, let's say, a self-driving car. So in general, a self-driving car has, let's say, this is the car, these are the front wheels, and there's generally a camera that's placed on the front and also the back. There's also an ultrasonic sensor, which works by sending ultrasonic waves around to detect proximity. There are also LiDAR sensors, which are more sophisticated, which can take into account, you can essentially get a point cloud and generate a 3D environment based on your LiDAR sensor. And because they sometimes also rotate, well, most of the times they rotate, you can get a 3D representation of the world around your vehicle. And then you also have radars, which have a longer range than LiDAR, but are not as accurate as LiDAR is. But you can use this for like collision detection of something maybe 100 meters in front of you, 200 meters in front of you, and make decisions very quickly. But each of these different sensors have different amount of data requirements. So, for example, radar sensors, like if you have 4 to 6 of those sensors in your vehicle, you will generate about 0.1 to 15 megabits of data from each sensor. And then from LiDAR, because LiDAR has a lot more information, you're gonna have something which takes three-dimensional information by sending lasers out. It's a bit more sophisticated, and then you would be using basically 20 to 100 megabits per second of data being generated. And cameras are by far the most data heavy. So because this is, as you all know, it takes a lot of bandwidth to stream a live video, and this is same the case when it comes to cameras in self-driving cars, generating about 500 to 2,500 megabits per second per sensor. And then ultrasonic sensor, which is by far the smallest, which require only about 0.01 megabits because it's a really little bit of information coming from the ultrasonic sensors. Vehicle motion sensors, GNSS and IMU, which are more motion related, it can sense the motion of the vehicle without using sensors. So for example, using GPS satellites also use some amount of data, but also quite less compared to the first three. But in total, if you're looking at a self-driving car, they are basically generating essentially 3 gigabits per second, which is a lot of data. And essentially that means you need to store about 1.4 terabytes of information every hour, or maybe even 40 gigabits per second. Depending on the type of system that you have, you could be having as little as 1.4 terabytes generated per hour, or 19 terabytes per hour. So this is probably why Tesla decided to ditch radar and LiDAR. I'm not sure about radar, but they definitely ditched LiDAR in favor of just using mostly just camera and radar. Because not just having this complexity and additional weight of the sensors on your vehicles, you also have to pay for a lot of data. And because you really have to put cameras anyway, so maybe they decided to just use their cameras for the self-driving cars. And who knows over the long term what would have been the right decision. But maybe the LiDAR systems in the future are going to prove to be way more reliable than something that just depends on the cameras. So there are other challenges that come to the fray when you're talking about these cloud services. Or big data services, and it's about scalability. So sometimes you have let's say you have a giant problem, which you like to, which you know that you can divide into multiple tiny parts. But then you also know that you only have certain amount of nodes that can solve this problem. So ideally you can just split that problem into very equal parts, and then also give this problem into your tiny other nodes that can then solve this problem, and then collectively you have a solution to your larger issue. You also have, let's say, in parallel processing, you have this issue where you have a giant process which can be divided into a bunch of tiny processes, and you know that these are different resources that need to be accessed by each of your processes. That ideally you can say, okay, you only have this resource being accessed by this sub-process, so you can assign each of them in advance. But in practice, what really happens in these systems is really more complex. Sometimes some resources are not available. Sometimes some nodes for computing are not available. So in practice, you might have to use one system to do multiple things, or one resource needs to be accessed by multiple different sub-processes at the same time, which comes to asynchronicity. And you need to make sure that sometimes write operations are synchronous and not asynchronous, because um, you need to make sure that no race conditions occur. So you have a lot of different problems when you try to scale your problem. So if you have one tiny problem which you now have to replicate over here 6 different cases, you don't really always get the ideal scenario where, okay, I buy one extra device, one extra processor for every single device that I have to do it again. You still have some dependency issues because you're not able to store all of your data in one place anymore, and there is an additional overhead that takes place which makes it very hard to scale your services over a larger larger terrain. So when it comes to fleet management, it's very hard in practice to always maintain your one-to-one ratio of resources to compute resources, which is why it's a lot of difficulty that happens to when you come to big data. We have a lot of slides here that you can look into on your own time when it comes to machine learning. So the reason why we are talking about machine learning in this lecture here is because it doesn't matter how much data you have. You generally, if you want to make sense of what this data is and how to use this data, you have to apply some kind of intelligence to it. And depending on your problem, you're going to use a different type of artificial intelligence. So the most basic type, you could use some kind of deduction, reasoning, or problem solving approaches. And then you have machine learning systems, which also allow you to represent your knowledge in very new and complex situations. So you might already know there we talk about supervised and unsupervised learning in machine learning. And when it comes to planning, if you're, let's say, self-driving car, when it comes to motion manipulation, you want to have some type of AI that can do certain actions inside of your systems. And then there are also perception tasks, which comes under computer vision and social intelligence, that allow your system to also do more complex actions based on perceiving, let's say, camera information. And then there are these more complex ones known as reinforcement learning, which are even its own giant subdomain where you're using kind of a little bit of everything to basically perform or learn to do certain actions based on trial and error. We're going to go very briefly over these slides because we're not going to go into too much of detail because these are for your self-study. But briefly, we are having some information about supervised learning, where you are assigning data to classes, or you learn to classify your data into different predefined classes. And unsupervised learning, where you are trying to cluster data or try to figure out underlying structures and relationships amongst data that you have collected, where you may not know what information may be under the layers. You don't have to label anything, so there's no amount of data. The training is a bit easier in this case, and it helps making sense of underlying patterns in your data. But the disadvantage is that it requires a lot amount of data to do this. And we have some examples here for unsupervised learning, and also particularly clustering approaches. You do different things based on the type of clustering approaches you have. You have something called as partitional clustering, where you define how number of clusters you have and then iteratively check if this is very good, and there is a very good intra-cluster separation or intra-cluster distance, and making sure that you are iteratively increasing the amount of distance between your clusters and decreasing the distance between nodes within a cluster, and then iteratively arrive at k defined clusters. And then you have something known as hierarchical clustering, where you are not defining per se the number of clusters you have, but over a period of time you start with many clusters, or start with only one cluster, and then over time arrive at a number of clusters based on how well you can have the distance between each points. And then you have something known as a density-based clustering, where you basically define how far away from a certain point do you consider that this point is no longer part of a cluster. And the benefit of this approach compared to the other ones is that you don't have perfect circles around your data points. You can have more complex shapes arriving outside of your clusters, for example in this case here. And then you have something like model-based clustering, which is more statistics related, where you basically say you're applying a statistical probability of a certain point being within a cluster, and then you're applying very specific methods to do this, for example using Gaussian mixture models. Reinforcement learning, like we said, used also, it's not an unsupervised method. It's basically separate from supervised and unsupervised learning, where your machine learning agent is able to perform certain actions inside of your system, and for every action they do, they are rewarded or given punishment. So over time, this reinforcement learning agent is learning to do the correct action to make sure it maximizes the expected reward over an extended period of time. And this is something that is heavily used in training autonomous systems like self-driving cars, but they are quite complex and very hard to train because you have to pre-simulate a lot of different scenarios and different types of actions that it can do. So imagine a self-driving car, putting it into a road and then asking it to learn on its own. It's going to crash into a lot of people. Sure, it would be punished, but you're going to be hurting a lot of people at the end of the day. You could argue this is what Tesla does, basically like using its users as the beta testers. But on the other hand, reinforcement learning is very, 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 very beneficial from getting real sensor data and real actions and real systems. So it's a very, very good technique that you can use when you are able to do actions in your system. We have some more examples on exactly how reinforcement learning architecture can look like, and something like k-nearest neighbor, which is another type of classification technique. And now going on to something that we want to go into the deep about, called data analytics. And data analytics basically is the process of inspection, cleaning or preparation, and then transforming and modeling your data for the purpose of extraction of useful information. So the whole point of having data in the first place is to extract useful information out of it, and this is what data analytics is. And the extracted information is the basis for any subsequent decision making. So if you don't have data in the first place, you cannot extract any information from this, and if you don't have information, you cannot make any decisions. So the whole thing that governs how much data you're going to have, how much processing power you're going to apply to extract this information from this data is basically decided by what decisions you would like to make in your system, and what kind of decision making resources do you need from the system to help you have a good outcome. And very often data analytics comes in with data visualization, because when you visualize what your data looks like, you can kind of see the type of information and knowledge that you can gain from these systems. So the value of your collected data depends entirely on their interpretation and the decisions that are made on the basis of this data. So it's very important that we are using the correct techniques when it comes to the analysis of your data. So we have seen this image before. Like we said, we have a lot of connected resources like IoT devices which are collecting a lot of data, so sensing a lot of data, creating some data here. And then your information comes from giving context to this data. So some amount of processing, and then given some existing knowledge, you can have some meaning from this information, And then given synthesis, you can convert this into wisdom. And looking at this from the other way around, if you want to know how can use of a resource be optimized dynamically, you first need to do something like collect information about what happens to this resource, then try to diagnose how did this happen to the resource in the first place, and then try to discover what better use can be made of the resource given current conditions, and then predict the conditions in the future. If the condition in the future is going to be in this way, how can I optimize it dynamically? So this is something that you can have increasing ability to support your human decision makers. And essentially it starts at the very bottom of the ladder when it comes to collecting your IoT systems, and then your big data, cloud, and fog computing, and then using your machine learning and AI models. So all of the different things that we've talked about over the period of this lecture course on IoT is kind of collectively explained by this slide here. So we talked about the basics of Internet of Things, about wireless sensor networks and how they are important, and how we collect data from them. And then we also talk about today a lot about big data, cloud systems, and fog computing, and then also where AI and machine learning takes place. So AI and machine learning is something that we really use to figure out what happens to resource, predict also how to do different things in the future differently, and then also give you some help with decision making. It's something that we use AI for, and integration is generally something that you always do for the cloud, where you have the information, and data collection obviously is something where you do over the at the very, very edge of your system when it comes to the IoT devices. And an overview of the process of this whole data analytics pipeline. So you're taking information at the very, very, very beginning. This is quite easy. So you see in this graph, the more towards the right you go, the harder it is to do these things. So descriptive analysis, just telling you what happened, is quite easy. You can just take sensor data, and there you have the descriptive analysis. Diagnostic analysis gives you the ability of hindsight. You know that something happened and you want to know why something happened. And this is something that you can only do with your descriptive analysis, something that you do after. And predictive is something where, given insight from your diagnosis, you know that you can predict what will happen in the future, and then maybe with some foresight of this prediction, you can then have prescriptive action. What can I change over the current situation, whereas I can optimize the correct outcome in the future? So these are more and more difficult as we are going up the chain, but also the value of doing those also increases. So depending on the resources you have, you want to go as much up the chain as possible to get as much value from the system as much as possible. Here's one example of data processing when it comes to the big data. So you generally, when you want to have when you're collecting a lot of data from the cloud systems, you might collect a lot of different things in different input streams. Let's say you have a lot of data collecting with, in this case, tokenized by just random words. And let's say the operation that you would like to do is count the number of instances of each of these words here. But the problem here is you'd like to have this as fast as possible. So instead of just having one processor count every word coming from every single input stream, which is definitely possible, but when you have millions of data streams, it's quite hard. So what we like to do in the parallel processing systems is like to split your input data into multiple streams. So for example, here you take some data here, you put it into one data stream, and then similar for the others. And then you map those to what you actually want to do. Your function for counting something is basically then counting in this input stream the number of instances of each word. In this case, deer, beer, and river are just individually ones, similar for the other ones. And what it doesn't do, for example, is count what a word is. It doesn't add to each of the counters. So as you see here, even though car is represented twice, it's only given the value of 1. So mapping it is basically mapping each word to a number, and in this case you're mapping each word here to the value 1. And then to shuffle them, what you do is whenever you have the common different words. So as you can imagine, this is like a Python dictionary where each word has a particular value assigned to it. What you do is you take this dictionary, you call each of your different resources and get each of those different words and shuffle them to different places. And then you have 2 instances of bear, 3 instances of car, deer, and river. And then you reduce them. So now it's very clear that there are 2 bears because there are 2 of this particular word inside of this node here, and then very simple, you reduce them in each case, and then at the final result that you have is you have a computed list of number of words in this input stream. This is a very, very simple example. MapReduce is quite complex. It's kind of an intuitive example of how MapReduce works in giant cloud systems. And we're not going to go into too much detail about exactly how you would use this in practice. Another example of visualization of your big data. So this is a website which shows the number of users and number of sessions of a particular website. And you can see over time that there were a lot of different sessions going back about a year. And you can see that around here, I'm not sure what month that is, there were a lot of viewers for this particular website. And then over time, it was kind of similar over time. And then suddenly, April 2017 or something like this, it experienced a tiny trend towards having more visitors to this website. And we know that most of the visitors that are coming to the website are like new visitors. So there's only 22% of retention of this website. So maybe if you want to have more audience retention, you might want to change something in your system to make sure that the new visitors you have are staying and coming back for more information or whatever service you're offering from this website. So having some kind of visualization for your different system. This is just an example for a website, but having different visualizations for your big data systems is very, very beneficial because you may be able to collect a lot of nice information and knowledge and allow you to make decisions in the future regarding optimizing, let's say, the number of visitors you're having over time. Predictive analysis is basically something, or predictive analytics when it comes to big data analytics is something where you have classification of new observations on the basis of training data from the past. But you are not really it's not really a question of predicting the future. Instead, you calculate the probability of the non-occurrence of an event with a certain degree of reliability. So you don't say what the probability of something happening is. So you cannot say that, okay, I'm 90% sure that this is happening, but you actually want to know that I want to know the probability of something not happening. So this is very, very important to do in risk management scenarios. Let's say COVID happened and you have a analytics platform that goes into looking at the supply chain of your system, and you actually want to have the probability you try to calculate the probability that you don't have a shortage of a certain resource inside of your supply chain. And this is a it's like a risk management strategy and making sure that outliers, like very, very seldom occurring events, like let's say a certain batch of a certain product being contaminated or a break in your supply chain, is not underrepresented inside of a data set where you're doing a lot of analytics. So these tiny events, which only happen some of the time but cause a lot of damage, need to be handled separately. And basically this comes into your predictive analytics and you use them for risk management and risk assessment. One example of this is here. So this here is an image coming from a crankshaft of an engine. What you basically have here is an engine which broke apart at the crankshaft, which is something that so the pistons in an engine are driving this shaft in the middle, based on these different combustion loops. And this thing that actually, the first thing that causes the first thing that converts this chemical energy from mechanical energy to rotational energy is this thing called the crankshaft. And during this process, there are a lot of push and pull in the system. There's a lot of high stress because basically these are giant explosions or tiny explosions happening inside of your combustion chamber. And a lot of vibration from your engine parts causes over time some damage to your system. And over time, they can basically snap off. And maybe one day you put too much power and then you end up snapping your crankshaft and you have to basically completely redesign or rebuild your engine from the ground up. So what you can do for predictive analytics is have an analysis of the measured vibrations of your system. In this case, the type of AI used is called a fast Fourier transform. I'm not going to go into details about how this works. But over times, you can say that there are increasing deviation from the so-called normal values or the factory values. And if you are measuring vibrations over time for a system, you can predict the quality and deterioration that you're going to have over time. And this is an example of predictive analytics where you can predict the possibility of non-occurrence of your crankshaft getting absolutely destroyed. Now, real-time data analytics is something which pertains to when you analyze your data. So sometimes you can handle your data after it's occurred. So in this case, you can take your data in, you can store it for a certain amount of time, and then your machine learning algorithm is applied at a certain time, and then you can analyze this data as you see fit. But sometimes some events are important. So you kind of need to have a lot of real-time analytics happening to your data so that you can make decisions also in real time. So the problem when it comes to real-time data analytics is that you need to process sometimes continuous data streams and answer questions without any delay. So one example that you already said is, for example, e-commerce order processing, like something where something happens in a supply chain and you want to immediately make sure that your order is deleted or it's not allowed to go forward. Or also, for example, in electric vehicles or self-driving vehicles, you want to process that a collision is happening very, very quickly and make sure to take evasive action before something like this occurs. So something where you have to collect a lot of different types of data. We talked about the different types of data that an self-driving vehicle can collect. So a lot of different types of data streams and answering question like, am I going to be in a collision without any delay or minimum delay? So there are different processing properties that we have to take into an account. So you need to take results for a particular question based on only current data. So you're not looking at data from a long time ago. Maybe your machine learning algorithms are trained on past data, but the questions that you're going to be asking are only based on current data. And you calculate this result on individual data sets for a very small time window. For, let's say, a self-driving car, like the time window is basically milliseconds at many times. So you don't want to be making decisions to swerve out of the way after a few seconds. You want to make those decisions in milliseconds. And you optimize these data analytics tools for low latency. So calculations are close to real time are often quite simple. So let's say the decision to change a lane because a certain car is having an accident in front of you, or let's say a car is slowing down in front of you, is basically a decision made to just avoid a collision. It's not really a decision that is made to save you time, but let's say there's a collision maybe several kilometers in front of you, is something that you are not taking in real time. It's something that's more complex that you have to change your route and so on and so forth. It's something that requires more complex calculations. So real-time calculations are quite simple, at least in relation to more complex big picture calculations. And some of the things from the business end that you can do is something like Apache Storm or Amazon Kinesis. So we've already talked about a lot of the AWS systems before, and the place where real data analytics comes in is this thing called Kinesis. Obviously, also costs a lot of money to do so. So this brings us to the end of IoT and big data. We hope that this was an informative lecture for all of you. You're going to take a tiny 15-minute break and talk about exercise 7 or any questions that you have. So because last week we had essentially 2 lectures within the same lecture period, the second part of last week's lecture, which was IoT security, is what we have as a lecture for publishing today. So we remember that we gathered data from different sources in exercise 5, different sensors, and then we put them into one data set. And then in exercise 6, what we did is we processed the data to have predictions. So the amount of electricity generated by your, let's say, your wind turbines or your solar panels. But so far, we are not really looking at the aspect of privacy and security. And like we said, that privacy and security is something that you need to do from the very beginning. So what we're doing is we're adding a layer of privacy and security when it comes to handling related data. So what we're going to do is simulate a data handshake. A handshake in this case is something where you are trying to exchange data with a peer without a secure communication medium. So a communication medium which we know that might be tamperable, and it might be prone to data manipulation, especially in wireless networks. So your sensor data might contain sensitive information which are not meant to be public, or some other information, and therefore you need to encrypt this data against manipulation, and maybe also you need to sign some information to make sure that the correct people are able to read this data, and then also the correct people are able to give you this data. Like I said, we're going to take a quick 15 minutes break, and then we're going to go on to some questions we have from today's lecture or from the exercise. Thank you for your attention, and see you in 15 minutes.